Now, I want to look at applications of convection current in ventilation, then cooling of motor car engines. I want to start first of all with ventilation. The room is ventilated in this process, in this process of convection currents. Air heated by respiration as you breathe out and fired, could be from your kitchen, rises up toward the ceiling and escapes through the ventilators placed near the ceiling, while fresh and cool air from outdoors enters the room through the windows. So we'll have it that if you have in your kitchen, what's called chimney in your kitchen, through there you can have smoke passing through. For instance, those of them that yes, those of them that you use something like firewood in the kitchen, you have it that the smoke will pass out through there. Even hot air from the kitchen rises up and goes out through the chimney side. While you have it that the outdoor, the fresh air from outside comes in through the door, comes in through the window to cool the room. So we have it that the room is being ventilated in this process. We have air heated by respiration. We have air heated or produced by respiration or fires rises up towards the ceiling and escapes through the what? Ventilators placed near the ceiling, even in your room. So while fresh and cool air from outdoors enters the room through the what? Windows. So through the windows you have the fresh air coming in. Through the doors you have the fresh air coming. While through the ceiling, through the ventilators placed near the ceiling board, you have it that the hot air or heated air will do what? Will rise up and escape through such places. So through this, you can now get your room ventilated. It's one of the applications of convection current. Now, cooling of motor car engine. The engine of a car needs to be cooled to prevent overheating of the car. The heat generated by the engine is conducted by the metal to the water in the radiator. You know that the engine gets heated up. And as it gets heated up, the metal, the part of the engine made of metal, they will also have the heat, they absorb the heat, and the heat will be conducted now from the metals into the water which is in the water radiator. And the water in the radiator now is meant to cool the engine of the car. But now if you look at it now, it becomes hot because it has conducted the heat energy from the metal. So the water itself is cooled now. You have to cool it so it will be able to cool the engine of the car. So the water itself is cooled by the air created around the radiator by the motion of the car. I mean, as the car is moving, it also brings about air that moves around the world radiator of the car. And also the movement of the fan, the fan engine of your car also brings about cool air so as to cool the water in that radiator, because the water in that radiator is meant to cool the engine of the car. So through this process of convection, the engine is cooled. So through this, we'll have that the engine of a car can be cooled by convection current. Now I want to look at the next topic, the next mode of heat transfer known as radiation. It is the transfer of heat energy from one place to another without a material medium, whereby you can transfer heat can be transferred from the region of hot temperature to the region of cold temperature without a material medium. Just like that of conduction will have solid materials, that of convection will have liquid and gases at the material medium. The material media, they are both in radiation. There is nothing like material medium. It passes through a vacuum. In radiation, heat flows through a vacuum and no medium is required, unlike conduction and convection, as I have said before now. There is a vacuum between the sun and the Earth. You know that we talk about in outer space or space in between the planets, there is a space, empty space between the planets. So even between the Earth and the sun, there is a vacuum. So heat from the sun reaches the Earth's surface through that empty space in the process known as radiation. So we'll have it that the heat from the sun gets to us here on the planet Earth through the process known as what? Radiation. So no material medium is required. In a vacuum, we get the radiation from the sun. Now, detection of radiation. How can we detect radiation, presence of radiation? A thermopile can both detect and measure radiant energy. So we use an instrument known as thermopile. It can be used to detect and to measure the amount of radiant energy in a particular environment. Note that good emitters of radiation are also good absorber of what? Radiation. Good emitters of radiation are also good absorbers of what? Radiation. Experiment to compare heat absorption by two surfaces. We want to use this experiment to compare heat absorption by two what? Surfaces. You have this surface here, you have the other one here. Here is a dull black surface. And here is a polished surface, shiny surface. Then you have light placed in between two of them. Then you have a cork material attached to this object here, to this object here. We'll see which one falls out first as we go ahead in explaining this experiment. In this experiment, two copper rods, these are the copper rods here, of the same length and the same cross-sectional area, of same thickness are used. One is painted black, that's this one here, painted black, and the other is polished so that it is shiny, that's one here. Wax is used to attach a piece of cork to the opposite sides of the rod. So we use wax to attach a piece of cork to the opposite sides of this. You know about candle wax. So we use it to attach this cork to the opposite sides of these rods. The two rods are vertically a few centimeters apart. So you can see them they are at the same cm apart, but few centimeters apart so that they can absorb the heat coming. A source of heat is placed midway between the two rods to ensure that both receive the same amount of heat. So this is the source of heat placed at midpoint between two of these so that they can absorb the same amount of heat energy. Now I want to look at applications of convection current in ventilation, then cooling of motor car engines. I want to start first of all with ventilation. The room is ventilated in this process, in this process of convection currents. Air heated by respiration as you breathe out and fired, could be from your kitchen, rises up towards the ceiling and escapes through the ventilators placed near the ceiling, while fresh and cool air from outdoors enters the room through the windows. So we'll have it that if you have in your kitchen, what's called chimney in your kitchen, through there you can have smoke passing through. For instance, those are things that those are them that you use in something like firewood in the kitchen. You have it that the smoke will pass out through there. Even hot air from the kitchen rises up and goes out through the chimney side. While you have it that the outdoor, the fresh air from outside comes in through the door, comes in through the window to cool the room. So we have it that the room is being ventilated in this process. We have air heated by respiration. We have air heated or produced by respiration or fires rises up towards the ceiling and escapes through the ventilators placed near the ceiling, even in your room. So while fresh and cool air from outdoors enters the room through the windows. So through the windows you have the fresh air coming in. Through the doors you have the fresh air coming. While through the ceiling, through the ventilators placed near the ceiling board, you have it that the hot air or heated air will rise up and escape through such places. So through this, you can now get your room ventilated. It's one of the applications of convection current. Now, cooling of motor car engine. The engine of a car needs to be cooled to prevent overheating of the car. The heat generated by the engine is conducted by the metal to the water in the radiator. You know that the engine gets heated up. And as it gets heated up, the metal, the part of the engine made of metal, they will also have the heat, they absorb the heat, and the heat will be conducted now from the metals into the water which is in the radiator. And the water in the radiator now is meant to cool the engine of the car. But now if you look at it now, it becomes hot because it has conducted the heat energy from the metal. So the water itself is cooled now. You have to cool it so it will be able to cool the engine of the car. So the water itself is cooled by the air created around the radiator by the motion of the car. I mean, as the car is moving, it also brings about air moves around the radiator of the car. And also the movement of the fan, the fan engine of your car also brings about cool air so as to cool the water in that radiator, because the water in that radiator is meant to cool the engine of the car. So through this process of convection, the engine is cooled. So through this, we'll have that the engine of a car can be cooled by convection current. We have a black painted car. It will absorb more heat, and the heat will be retained in the interior part of that car. What if you have a brightly painted car? It is preferable because it will help to radiate or reflect, to have to reflect away the light or heat energy coming from the sun. And it will be comfortable for you to be in such vehicle. So it is preferable that you have a brightly painted car in hot tropical countries like Nigeria, so that you don't feel uncomfortable inside your car in sunny days. Firefighting suits worn by firemen is bright and shiny so that it does not absorb much heat to burn them. So it's also applicable here. That application of radiation is found here. So having a firefighting suit worn by firemen is bright and shiny so that it does not absorb much heat to burn them. So this does not allow heat to retain inside their body. So this material is always bright and shiny, and it will not allow much heat to be inside their body. Also, the interior of stoves that you use to cook in your kitchen are painted dull black to provide the high temperature needed for heating your water. Remember, dull surface absorbs the heat. I will not allow it to move out easily, and so it will absorb it and keep it there, so it will be able to give the stove give it a high temperature needed for you to heat your water or cook your food. Now we'll see another place where this radiation is also applied. We have your heat transfer is also applied in thermos or vacuum flask. Heat transfer in radiation is also found in thermos flask or vacuum flask. The image you have here is image of a vacuum flask. Now let's have a wider view of the vacuum flask. So we'll have here the vacuum flask. These are the parts, the silver surfaces. Have 1, 2. You have the cork here. You have the vacuum seal. You have the cork supports. It supports holding this vessel here. You have the liquid inside. It could be your hot water or your hot tea. You have the metal casing. You have the vacuum in between the silver surface here and this metal casing, the vacuum here. You have the cork again, a cork here as a cover. As we go ahead, we'll get to know the function of each of these parts and how this can reduce heat loss either by radiation, convection, or conduction. The thermos flask is an instrument designed to minimize heat loss by conduction. It is designed to minimize or reduce heat loss by conduction, convection, and radiation. So it keeps hot water hot and cold water cold. Meaning that if you decide to drink cold water in the afternoon, you put your chilled water there, it will retain the temperature of that water until the time you want to make use of it. If it's hot water you want to use and take your tea any time of the day, it will still retain the temperature of it. That is what it is meant to do. It consists of a double-walled thin glass with a vacuum between the walls. It's a double-walled thin glass, double-walled thin glass. This is the double-walled thin glass with a vacuum between the walls. Consider there's a vacuum between the walls. The vacuum releases heat lost by conduction because it does not touch the metal casing there. So the vacuum releases heat lost by what? Conduction. When there is vacuum, there is no air there. So there is no how the hotness of that, or the temperature, the hotness of that water can be reduced. So there is no how the heat can be lost through conduction because there is a vacuum there. Between the silver surface here and the metal casing, there's a vacuum. So there is no how heat can be lost to this because there's no contact. So there's a vacuum there, so it reduces what? Heat loss. By convection, there is no air here. There is no liquid here, so there is no how it can be lost out of this silver surface here or this vessel inside here to the metal casing. So through this, it tries to reduce heat loss by conduction or what? Convection. And the double walls of the glass vessels are highly polished and silvered also. The polished nature, it is highly polished and silvered on the vacuum side so as to reduce heat loss also by what? Radiation. So it tries to reduce heat loss also by radiation because of the highly polished and silvered nature of this double wall. So the vacuum there tries to reduce heat loss by conduction, as I've said before now, because it will not touch the metal casing. Now, by convection, because there's no air in between them. Another one here is that we mentioned about that the glass vessel, the double wall of the glass vessel is highly polished and silvered, and so it reduces heat loss by what? Radiation. Then we'll have it also at the bottom of the flask rests on the cork supports. You can see it here. It is resting on the cork supports. And the mouth of the flask is also closed by a cork stopper. Look at it here. So we'll have it that heat loss by convection is being prevented by the use of tight-fitting cork as cover. So this tight-fitting cork, which as the cover, tries to reduce heat loss by convection. So heat does not get lost out of the heat is not lost through this thermos flask by convection as you cover this flask with tight-fitting corks. So these are the different ways by which this thermos flask can prevent heat loss by conduction, convection, and radiation. So we've come to the end of this. Before we get to the end of it finally, we want to remind ourselves of what we have learned before now by evaluating what we have done so far from the beginning of the topic. The questions we have here are: 1, give 3 differences between heat and temperature. Give 3 differences between heat and temperature. Number 2, list 3 effects of heat energy when added to an object. What are the effects? List 3 of them. List 3 of them. Define the term linear expansivity. List 3A. 3B, apparent cubic expansivity of a liquid. Hope you've written that. Number 4, list the 3 methods of heat transfer. Number 5, an iron rod has length 50 meters when the temperature is 20 degrees Celsius. By how much will it expand when the temperature rises to 30 degrees Celsius? Take the linear expansivity of iron to be 0.000012 per Kelvin, or 1.2 times 10 to the minus 5 per Kelvin. This is the same with this. Now I want to look at the answers to this question. I hope you are following. Number 1, you have to list 3 differences between heat and temperature. You have to list this. So number 1 will have, in a tabular form, first column you have heat energy, second column you have temperature. The first one is heat energy is a form of energy that brings about sensation of warmth, the feeling of warmth. The kind of energy that brings about that, we've said it, is known as what? Heat energy. While temperature is a measure of the degree of hotness or coldness of a body. The measure of the degree of hotness or coldness of a body. How hot a body is or how cold a body is. The measure of the degree of such hot or of the hotness or coldness of that body is known as the temperature of that body. Now, under heat energy, the SI unit of energy is joule, while the SI unit of temperature is Kelvin or degree Celsius. Number 3, under heat energy is a derived quantity, while temperature is a fundamental quantity. You can still find other differences by yourself as you make more research on this. Number 2, you have to list 3 effects of heat energy when it is added to an object. What are the effects? Number 1 is that it leads to the following. It leads to 1, change in temperature of the body. If you add heat to an object, it increases the temperature, and it can still lead to expansion of the body. For instance, you're cooking something like rice. If you add heat, the size will rise. Expansion of the body. Something like metal objects also, expansible ones, the body of such objects will expand. It can lead to change of state of the body. You will have ice block. It's already in a solid state. You add heat to it, it will melt and turns to liquid state. Add more heat, getting to what it is at boiling point, it now gets to gaseous state. So it leads to change of state of the body. Number 3, you have to define the term linear expansivity. Linear expansivity of a body is defined as the increase in length per unit length per degree rise in temperature of the body. We already discussed this before now. You have to also define the term apparent cubic expansivity of a liquid. It is the increase in volume per unit rise in temperature of the liquid when the liquid is heated in an expansible vessel. So we call that one apparent cubic expansivity. You're only asked to define them. Now, number 4, you have to list 3 methods of heat transfer. That is, number 1, conduction, convection, and radiation. These are the modes of heat transfer. Question number 5. From the question, we'll have it that the original length is 50 meters. The theta warming, the initial temperature there is 20 degrees Celsius. And you have to find the extension or the expansion of this or extension produced. Then you have here that final temperature is 30 degrees Celsius. While your linear expansivity there is given to us 1.2 times 10 to the power minus 5 per Kelvin. So we have this formula that alpha is equal to L2 minus L1 all over L1 into change in temperature, meaning expansion produced all over the original length times change in what? Temperature. Now, we don't know about the expansion rate because we don't have L2. I have to find expansion here. So alpha is now, you now have this E now is representing L2 minus L1. Since we don't have L2, we can use E expansion to represent L2 change in length, meaning expansion now. E now represents L2 minus L1 is expansion E. So alpha is equal to 1.2. We're substituting now. To substitute these values into this formula, we'll have 1.2 times 10 to the power minus 5 is the linear expansivity. Is equal to E, we don't know expansion yet. Original length is 50. Final temperature is 30. Initial temperature is what? 20. So we'll have 50 into 30 minus 20. 30 minus 20 is already 10. So we'll have, now if you cross multiply here, you'll have 1.2 times 10 to the power minus 5 times 50, which is this, times 10. 10 is from 30 minus 20, which gives us 10 here. Now 50 minus 10. Are you following it? Is equal to what? Expansion produced. So if you multiply all these values here, you have 1.25 times 50 times 10 is 500. So this multiplied by this gives you 0.006 meters. That's the expansion there when this heat is being applied. So that brings us to the end of this lesson. Thank you very much. See you next time.